So this is where we were on Friday. I asked you to write these 3 bullet points down. We didn't spend a lot of time with the reduction potential table. We will, not even today, but starting tomorrow. In fact, tomorrow I'm going to give you a copy of the reduction potential table. For today, we're just going to have to look at the one in the book. But starting tomorrow, you'll have the paper in your hand, and I'll give you lots of practice with that, using that table. We did this on Friday, right? Was this the last thing you wrote down? Okay. So, then, for today, we're going to just kick off our time today with an example from Friday. Find the cell potential. Remember this Greek letter epsilon represents the potential. The potential difference, also known as voltage, for a reaction. So I have this very simple chemical reaction. It's a redox reaction. We got something losing electrons, something gaining. I'm going to give you a second to write the chemical equation down, then I'll have to toggle off and we'll have to look at the table in the book. All right, now here's our table. I showed you this on Friday. Now, actually, this table, if I can zoom out a little bit, this is not the one that's in the end of the book. This one is in chapter 18. So there's 2 reduction potential tables. I think they're identical. One is just kind of shrunk down a little bit, but I don't think the one that's in the text left anything out. It's just made a little bit bigger in the end of the book. So a couple of things about this. Again, and I know it's real hard to read, but it said, standard reduction potential table. I don't think the word table is in there. Standard reduction potential is 25 degrees for half reaction. All of these that are on here are reductions. Now when I zoom in, and I'm going to zoom into the right column, that's where we'll get what we need for this thing. You'll notice that highlighted here with the two lines is the baseline reduction. That's the reduction of hydrogen ions to H2. That has a reduction potential of 0. And so the things that are above that are good at reducing. They're more stable when they reduce than when they were ions. Below hydrogen, those things are not very good at reducing. You say they have a negative reduction potential, which means that they were more stable when they were ions than after they reduced. So the reaction that I asked you to find the reduction, the cell potential of, what was reduced in that reaction, I'm trying to move the book so I have the reduction in the reaction at the very top of the board. That's it. There. Copper plus 2 electrons yields copper. I actually had that written on the whiteboard too, right over here. The reduction potential, I keep moving, I'm sorry. The reduction potential is 0.34. Remember what the unit is on this table? What is the unit? If I move up, can you see it? Yeah, it's at V, volts. That's how many volts. So that means the copper is willing to reduce because it has a favorable, a positive reduction potential. Now, the thing that oxidizes in the reaction that I gave you is iron. Iron is going from neutral iron to iron positive 2. Well, we'll need to find, remember this is a reduction potential, and I want you just with your eyes to scan down all these half reactions. You're going to notice the electrons are in the reactants for all of them. You see that? That makes them all reductions, because the reduction is the gain of electrons. If you need something to oxidize, you have to find it in the products on this table, and then take that half reaction and turn it around. If you turn the reaction around, that means that the electrons will be in the products, which is an oxidation. See what I'm saying? So we're going to have to find iron oxidizing to Fe plus 2. And it's on here. It's right there. This thing right here. I can zoom in a little bit more too. Whoop. Maybe that's too much. And yeah, it's right here still. So iron, again, this thing, you got to take and flip it over. And when you do that, the reduction potential, the reduction potential becomes the oxidation potential, but you need to change the sign on. So the reduction of iron plus 2 to iron is negative 0.44. However, if you turn it around to have iron oxidizing to Fe plus 2, that would have an oxidation potential of positive 0.44. Okay? So that's how we use this table. You can get the reduction values and the oxidation values, even though they're all given to you as reductions. Turn them around and make them oxidation. All right, so going back to the slide. So the thing that's reducing is the copper, and that has a reduction potential of 0.34. The thing that's oxidizing is the iron. It's got an oxidation potential of 0.44. So you just add those two together. Oh, that's pretty easy. So this reaction would have a cell potential of 0.74 volts. And one of the things that we need that's going to be really important for us to understand is that when you have a reaction that has a positive cell potential, that means the reaction is spontaneous. I think that you've picked up that we made kind of a big deal about whether reactions are spontaneous. All right, we good with that? I have well, pretty close to this reaction in the back. I want to demonstrate this to you. So I'm going to take this. Maddie, can I have you hold this for me? That might be too close. But I have a solution. Now, I messed this thing up, honestly. The reaction that we have up here is iron oxidizing to Fe plus 2. So I went back to the stock room and I got iron nitrate. I wasn't paying attention though. I got iron 3 nitrate, not iron 2 nitrate. So this is not going to give us the correct voltage. If we were to calculate it correctly, it would be iron going to iron 3. That has an oxidation potential of 0.04 volts. So the copper is still reducing. It would be 0.34. The iron would be oxidizing with an oxidation potential of 0.04. So if you add those two together, it would actually give us 0.38. 0.34 plus 0.04 is 0.38. So just to demonstrate that, this is my iron 3 solution, and in my porous cup, I have some copper sulfate solution. I could just show it to you. The blue means it's copper, so I'll put that in there. And this solution has been sitting in the porous cup since 4th hour. And I'm just going to use Arti as my demonstrator. I want you to just touch the outside of that cup. And what does it feel like? It's kind of cold. And does it feel like it's a little bit moist or damp? Yeah. It does kind of, yeah. I just do that to let you know. The walls are porous. This is seeping out of the container walls because the walls have holes in them. And it does that on purpose. They make it like this on purpose. This is a clay product. So you stick, my fingers are stuck, there we go. So I just put the porous cup with the copper solution right into the iron solution, and we need an electrode, so I'll take, it's very easy to get iron, just go buy a package of nails. They're made of iron, almost pure iron. They have a little bit of other stuff in them. So I'll just clean that off and put it into the iron solution. Iron serves as, the nail is my electrode for this one. And then I have a strip of copper, that looks like copper, and I'll put it in the copper solution. Now, my voltmeter is right here. And when I turn the voltmeter on, right now, my voltmeter leads are not touching anything, so it should read 0 volts. And as long as I'm not moving or doing anything, it says 0. So now, I'm going to take, let's see, the black is the direction. That's where the reduction is going to occur, which should be on the copper. You need good metal-to-metal contact on the voltmeter. And what does it give us? Now this is a little bit high this time. The voltage is about 0.51 volts. And it is dependent on the concentration. The table, we were getting these values from the table. The table is only good at standard conditions, which means 1 molarity and 25 degrees Celsius. I just dumped some of the iron nitrate into this. I didn't measure what its concentration was. The same thing with the copper. I just dumped some in and dissolved it. So if I had standard conditions, my voltage would be pretty close to what it should be. But this is how we set up a galvanic cell. Now I know that in the book it showed the 2 beakers. And in the book, I don't know, they use this elaborate setup where you got this bridge, this kind of partway up bridge between the 2 beakers. Man, those things would be super expensive. But that serves as it does the same thing as the porous cup does. So when it's time for you to create a battery, all this equipment will be available to you. You can use the glassware, you can use the porous cups, you can even use the U-tubes if you want to, if you want to do it like that. But yeah, you just have either your anode or your cathode on the outside, and then the opposite thing on the inside, and they'll work together, and the walls of the cup act as the salt bridge. So tomorrow, over the next couple of days, I have some other reactions that I can show you how we set those up and the voltage of those. It's pretty consistent, though. Thanks, man. Okay. So 3 things about that reduction potential table. The last one you probably won't like very much. I'll try to see if I can explain why it is that. That middle bullet point is why I didn't get the voltage I hoped to.